Again, thank you, Ronnie, for hosting me. Thank you for all attending. To start, my name is Michael. I'm at Stanford. I'm a fifth-year CS PhD student. And this is kind of what I wanted to talk about today. Basically, what are foundation models for electronic health record data, with a particular focus on the structured data within the electronic health record. So I'll start with some quick motivation about why you should care about this. Talk about the data itself, what is electronic health record data, and then go into some of the modeling choices people have made, as well as how we think about evaluating these models. And in terms of just kind of high-level goals for this talk, first, I just want to convince you that the approach, the foundation model approach, which we've seen so successful in so many domains, also makes a lot of sense in the healthcare domain, particularly for electronic health record data. Secondly, I want to show you as machine learning practitioners how simple and easy it actually is to take existing methods from the world of machine learning and translate them to electronic health record data. And then third, want to encourage you to do so and to do so on a data set that we published. So first of all, what are electronic health records? What are foundation models, and why should you care? So kind of the first motivation for working in machine learning for healthcare, or just healthcare in general, is that healthcare is hard, right? And so these plots show the health outcomes versus how much we spend on health outcomes. And you can see that the US is kind of an outlier here, right? So healthcare is not a problem where you just throw more money at it and people get healthier. They have to think a little bit more critically. And the data itself is very vast, very complex, and it's pretty much entirely unlabeled. I think the stat is the average hospital generates about 130 terabytes of data per day. This grows at a rate of roughly 50% a year, and roughly a third of the world's data is healthcare data. And labeling all this data is very hard, right? Even doctors don't know how to make sense of a lot of the data that they see. Otherwise, they diagnose everything perfectly. And so a key motivating question is, how do we learn from this huge amount of unlabeled data? And so the natural approach kind of in today's day and age is to throw a foundation model on it. And this is a foundation model is basically just a large machine learning model that's trained on a large data set. And we do this in a self-supervised or unsupervised manner. And this is appealing in the setting of healthcare for a few reasons. First, we have a ton of data, but unfortunately it's unlabeled and it's very hard to label it. Secondly, we want to do training at scale and we want to do it in some sort of self-supervised way. Third, we have a ton of tasks that we care about. And so we want our base model to be able to generalize to new tasks, like diagnosing any of the thousands of or tens of thousands of different conditions a patient might present with. And then fourth, again, because data labeling is so expensive, we want our models to be sample efficient. And foundation models in other domains have just established that they have these really nice properties. And so kind of the vision mapping this to healthcare is, we want to train a foundation model on health record data on this very large, mass of unlabeled data, potentially millions or tens of millions of patients. And then the hope is, we learn some model that then can be adapted to whatever specific downstream task you want. And oftentimes the downstream tasks you care about, you only maybe have a few examples of the patients you care about. So for example, pancreatic cancer, right? There's only a few hundred patients at Stanford with this disease. But at the end of the day, a pancreatic patient is still a human. And so their disease trajectory should share some sort of similarity with the other millions of patients that we see at Stanford. It makes sense to learn patterns here and potentially apply them to, name your downstream task of choice. And so that's kind of the vision for, how you apply foundation models to this setting. And then, what are some of the tasks you might care about? I'll just super briefly highlight the headlines here. Like, you could use these models, and this is not just foundation models, but just machine learning in general, to improve patient outcomes. So things like selecting treatments, diagnosing people. You could use it to improve the efficiency of the actual how the hospital runs, like predicting quality metrics like 30-day readmission, allocating resources, things like that. And there's also applications in research as well. But I'll share this slide, but basically just there's a lot of tasks that you might care about in a hospital setting. And then just last but not least, I'll get into this later, but why you should care about foundation models for EHR data. Basically, they're already kind of the state of the art on a lot of the clinical tasks that we care about. And so this approach is, if you're thinking about starting in, ML for healthcare or EHR research, this is a great place to start since these models have already demonstrated very strong performance. So I know that was kind of a very brief, very fast overview of the motivation and what foundation models are. I think one thing I wanted to double click in for this audience in particular is the data, right? All good machine learning starts with understanding the data, and the data in this case is very important to understand. So what actually is EHR data? Many of you, if you work in healthcare, will be familiar with this interface. This is Epic, which is a very popular electronic health record vendor. Basically, all of your health data that the hospital has is stored in what's called the EHR, or the electronic health record. And this is just one view of the vast amount of data which a hospital might have on you, which is stored maybe not just in Epic, but a number of other systems. And so some of the popular EHR vendors are at the bottom as well. This is a very complex view, and if you talk to doctors, they'll complain about working with these systems. But for our case, we can kind of abstract away the electronic health record and think about it simply as just a way to record events that happen to a patient. So I would encourage you, at least in this talk, to think about the EHR as basically just a timeline of events, right? A sequence of things that happen to a patient over time. And as you can see here, a lot of different things can happen to patients, right? You could have an insurance claim filed. You could have a diagnosis. You could have a medication, right? You could have a procedure done. All these different things can happen to you. But again, they're occurring to patients over time. And that's kind of a big consideration in medicine, right? Is we care about trends and, how people are changing, right? A lot of work in machine learning for healthcare has specifically focused on, I'd say, one of these rows here, which is text, right? Clinical notes. And the application is obvious, right? Because large language models work with text. And so clinical notes are just another form of text. So why not just apply LLMs to this? And there's been a lot of great work here, especially out of CMU with the bridge. But there's a lot of other data in the EHR that these models don't necessarily pay the most attention to. And that's all the structured data at the top here, right? Like ICD codes, CPT codes, basically, all the kind of tabular or structured information within the EHR. This is also referred to as coded data, just in case you hear me throw that term around. And so the focus of this talk will primarily be on this chunk of data. So the structured data within the EHR. Again, there's been a ton of great work with clinical text, but the focus of this talk will be about how do we mine insights from the structured data within the EHR. And again, there's a lot of interesting multimodal work as well. But just to keep things in the 30 minutes I have left, we're just going to talk about structured data. And so kind of revisiting the abstraction we thought about previously, a health record, it's basically just a timeline of events that are happening to the patient over time. And so we can very easily model this, or straightforwardly model this, as just a sequence of tokens, right? And so now we're back in machine learning land where, here's my EHR, and I'm just gonna, tokenize it as a series of events that are happening to the patient. Each different type of event gets its own token. And now all of a sudden we're just doing sequence modeling. Just to kind of double click what kind of the analogy with natural language is, with natural language, you have a book, you have language, you tokenize it, and maybe, it looks kind of like this. With electronic health records, just the same thing. Instead of words, we have like diagnoses codes, medication codes, things that are happening to the patient. We just tokenize it just like it's language. And then we also kind of have the concept of sentences. In health land, sentences are like visits. So like I visit the hospital and a bunch of things happen to me, and then I'm discharged from the hospital. I visit the hospital again, I get a procedure, I get discharged. So there's kind of an analogy to sentences. A unique thing about electronic health record data is there's this temporal component too, which doesn't quite exist in text. Like there's no sense of like, the word me and Ishmael are, a year apart, but the word some years are a second apart. Whereas with EHR data, that can very well be the case. And so that's kind of an interesting modeling choice or thing that you have to keep in mind when you're adapting these techniques for EHR data, right? Because you could visit the hospital 4 years ago and then not see a doctor for another 4 years. And then in terms of like what are documents, we think of that as like patients. So each patient is like a document of visits, and each visit is, a sentence of coded tokens that happen to the patient. And so just to kind of make this analogy very clear, natural language here is kind of where we look at in terms of, how we think about the data. And then for EHRs, the source is hospitals, which complicates things because you can't just pull it off the internet. Our unit of data is patients. And just to give you kind of a rough sense, one of the most popular public benchmarks is about 400,000 patients. Stanford, which is like a pretty small hospital, has about 4 million patients, a small health system, sorry. And then some of the very large data sets like Truven, which is insurance claims, has about 80 million patients. And so the scale of these data sets is a lot smaller when you're just looking at the structured EHR data than in natural language. So just to give kind of a rough estimate, so at Stanford, we have, about 4 million patients. There's about 5 billion total structured clinical events that are happening to these patients. And so, just kind of projecting it to like the size of the US, maybe like the whole universe of structured EHR data is maybe like 500 billion tokens worth of data. I don't know if that's true or not. That was a super rough estimate, but this is just kind of give you a sense of the size of like the data that we're looking at. And then just to kind of double click into Stanford Hospital specifically, like I said before, roughly about 5 billion clinical events happen to our patients. I believe this data set is like 20 or 25 years of data. It's about 3.5 million patients, and there's 4 million unique codes. So like 4 million unique types of events that happen to these patients. And then just to give you a sense of, how long are the timelines that we're looking at? How long are the actual documents? The average patient is roughly 1,350 unique clinical events, but there's a huge tail. So like the max patient has almost 1 million events happen to them. And so if you look at kind of the distribution here of number of events per patient, the x-axis here is number of events on a log scale. The y-axis is number of patients. Most patients we see very infrequently, but the catch is that the most interesting patients, the patients that we actually really care about making predictions for, are this kind of long tail of people who are quite frequent flyers at the hospital, right? Who have the most complicated conditions, who we've seen for a very long time. And so that can, kind of make the modeling a little bit difficult because most of your training data set is these super short clinical timelines, but the people you really care about are like this very long tail of patients here, which are the most complicated to do predictions on. So yeah, again, I'll share these slides, but just kind of want to give a sense of like the scale, the type of data that we're looking at. Okay, so before I get into the how do we actually build models for this, any questions about structured EHR data that I could quickly answer? Maybe I have time for like 1 or 2 questions. Okay, great. And I don't think I'm missing anything on Zoom. So now that hopefully you have just kind of a sense of this is what EHR data is, basically literally just think of it as like natural language. It's a bunch of sequences of tokens. The question is, how do we build foundation models on this data? So again, as I've hinted about very strongly in the last 10 minutes, basically, we're just going to reapply existing methods to EHR data and see what happens. So I thought the easiest way to do this was to kind of map elements of kind of the original transformer to EHR data. It's not going to be one-to-one, and obviously this is a decoder-only model, but hopefully this will just be kind of give you a sense of, I have this great ML method that maybe you've developed or some new architecture. How do I think about applying it to EHR data as like a benchmark in my paper? So the first thing we do, right, when we work with sequence models is, we're going to want to tokenize our data, right? We can't just throw the EHR into a transformer. And so this is very simple. Basically, there's a few ways to do this, but basically you're going to take each of these clinical events and map it to just a single token in your vocabulary. Super straightforward. So like ICD code /E66.1 gets a token. CPT code, blah, 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 gets a token. So that's how we tokenize it. Super straightforward. Obviously, you need to do a little bit of selection with your vocabulary since there's millions of these possible clinical events. And so you have to filter down exactly what you decide to tokenize. But at its core, that's basically what we're doing. And again, there's a lot of different ways to think about tokenization. I'd say in terms of literature, this is actually where most of the differences are. Like people rarely change the architectures. They really mostly index on how do I represent the EHR better? And so most papers that you read in the field spend a lot of time on the tokenization strategy. I won't get into this in a ton of detail, but I'll just highlight like the main question is like, how do you deal with the temporal component of the EHR? Like I mentioned before, right? Like you could visit the hospital in 2016 and be totally fine for 5 years and then see your doctor for a condition and have to go in every week after that. And so a question with modeling EHR data is how do you incorporate that temporal information into things? One way to do it is you just introduce tokens that are like, this is the 50-day token, this is the month token, this is the year token. And then, sometimes you want to add tokens to represent the start and ends of visits, like certain concepts you might tokenize. Basically, there's just a little bit of flexibility here. I don't think this actually makes a huge performance difference, but one area that people have thought about. So, and then the other thing I'll quickly mention too, which I thought was cool at work out of Ed Choi's lab, is instead of actually treating each, so up here is like the clinical event. Instead of treating each clinical event as like, its own kind of discrete thing, instead what they do is they look at like the English description of the clinical event. So ICD code / whatever is actually, something insulin, blah, blah, blah. And this medication code is actually defined as prescribing drug vitamin A route. And so they translate the clinical events into text, and then they just run a normal text-based large language model over it. So I thought that was kind of interesting as well. So a lot of choices in how you tokenize the actual EHR data before you feed it into the model. Yes.
So what about like values, like lab values?
Yes, that is a really good question. They spent a lot of time in the paper thinking about that. I would say it's not very satisfactory how we handle that, but I think the thing they found best was to just separate each digit into its own token and then work with it that way. But yeah, I think lab values is a good question, and I don't think people have solved it. Previous approach, yeah, typically the most common way, if you're not going to convert it into text, is to like decile it. So go through your entire training data set, look at every single possible value the lab can take, bucket them into deciles, and then each decile gets its own unique token. Yeah. Cool. Good question. So, okay, great. So we tokenize our input. Now we need to, generate embeddings. So, this is pretty straightforward. I'd say kind of the interesting thing about the EHR data, again, is like the temporal nature of it. So in addition to maybe adding tokens for time, you can also add time into the positional embeddings that you add to your tokens. And so here, I forget exactly which paper this is from, but here, instead of just doing straight positional embeddings like you would do normally for text, they also add like an age-specific embedding. So like the patient has this age, we'll give them an embedding for that. They do one for the visit number. So all the events within the same visit have the same, I guess they call this the positional embedding here. And so, you can play with that a little bit as well. And kind of the cool thing is if you actually look at the embeddings that these models learn, they actually kind of make semantic sense. So this was from a paper called Claim PT, and they just basically projected the embeddings learned for different diagnosis codes. And you can see like, these are related to diabetes, these green ones are asthma, the blue ones are depression. Like, there's some sort of clustering that makes sense here. Great. So, we've gotten our EHR into a format that we can throw through the model. So literally just throw it through the model, just, call dot forward, literally nothing new here. And then, after we throw it through the model, we're going to want to run some sort of training objective on it. And these are pretty standard. So, one thing that a lot of papers have done is just classic mass language modeling, kind of like, BERT style, where you basically mask out a token and you try to predict it. So, which ICD code is this? The model predicts it, and then that's your training objective. People also do, decoder only models and kind of the GPT style. So this here is next token prediction now, where instead of picking like a token in the middle of the sequence, I'm always trying to predict what's the next token the patient will have. This is useful, especially if you're trying to generate synthetic patient timelines, because now once I've trained my, MedGPT or my Foresight model, I can now, seed it with some patient timeline and have it generate like potential trajectories that the patient might have. Or I could use it to generate synthetic data and then share that publicly instead of my actual EHR data. Another one, I've seen one paper that did kind of a T5 style model, transform EHR. And then the last thing, which I'd say is probably the most interesting objective from a student in my lab named Ethan, is a survival modeling objective, where he actually takes advantage of the temporal aspect of the EHR in a much more rigorous way than some of these other objectives, where instead of just predicting, the next token, he's predicting the time to that token occurring. And so he actually learns like survival curves for a set of, I think, like 8,192 commonly occurring codes at each step of this timeline. And so then the nice thing is here, you can basically get like for each of these patients, each patient is a different color. What is the expected time to event for pulmonary hypertension or something like that? And then we've seen in experiments that this style model does better on longer term prediction tasks than some of these other models, which makes a little bit of sense because, this is only looking ever at the next token. It's not trying to predict future occurrences like very far out in advance. Question. Oh, numerical values. Okay, yep, answered that. Temporal institutional heterogeneity. Geneity. Yeah, I guess one thing I'd flag is, every institution has like kind of a different. So there was a question about what happens when different hospitals have different coding practices. So maybe one hospital says this ICD code is this disease, but another hospital says this ICD code is the same disease, and they're different ICD codes. That happens a lot in healthcare. That's why it's so hard for interoperability to be a thing. The answer is, I think people are still trying to figure out how to do that. But that is a big advantage of this text-based representation, because this text will generalize in a way that just looking at ICD codes that might be coded differently across hospitals will not. Because every ICD code, every CPT code has some sort of English definition. And so if you translate everything into text, every hospital's data set can get translated into text, and then you're just working with text. And so that was kind of the motivation for this tokenization strategy. It's easier to generalize this across different hospitals that might use different vocabularies for their coding practices. Good question. Okay, so we've gone through kind of the training objectives that people think about. Again, this is pretty much just standard stuff from NLP. Lastly, all right, we train the model. How do we actually do predictions? So one of the most common things to do is to just add like a linear head to your model, do some sort of pooling over your embeddings, and then say, okay, I'll fine tune this linear head for whatever task you care about. So, maybe it's risk of new cancer diagnosis within 1 year. And, here I'm just spitting out probabilities. So, that's, I think, also fairly common as well in other domains. The other way to do it, which I think is less explored in EHR world, is to actually roll out like future patient trajectories. So here, instead of just saying, I'm going to run the model, add a linear head, and fine tune it for this specific task, I'm just going to run my model forward and see what codes it generates. And I'm going to do this a bunch of times. And then I'm going to say, okay, their risk of mortality is however many timelines end in death before a discharge event occurs. And I've seen actually just one paper do this called Ethos earlier this year. But I thought that was cool because that doesn't require any task-specific fine-tuning. And that's more in line with how people use large language models today, right? Like you don't fine-tune a linear head on GPT-4 every time you want to do a task. You just ask it, hey, do this task for me. Is the answer yes or no? And it just gives you the answer. And so this approach in kind of a more zero-shot fashion is cool. And it also gets at some of the generative abilities of these models. Yeah. Any questions about kind of that setup before I get into some of the initial results that folks have seen? And sorry, I know this is very fast. But I think the main takeaway I just want to give a sense of is just like, this is like, you guys like should just take what you've already done and just apply it to EHR data. Not enough people have done that, but I think there's a lot of gains to be made from this. And I think the chasm between natural language and EHR is like much smaller than people think about. Obviously, you have to think carefully about the data, but I think there's a lot of opportunities to apply methods that already exist on this sort of data. Cool. So this is kind of how we build these models. So what do people actually see in practice? I'll start talking about some of the results. So the first nice thing is we're doing this with transformers, and so we have this nice attention block. And so this is from the Medbert paper, if I'm predicting something like type 2 diabetes, I can look at the attention and try to get some sort of interpretability out of it. And here we see that use of insulin is like a big predictor of this event, which actually, now that I think about it, is definitely an artifact of the data, because I don't see why this would help you make this prediction. But I think this is more of saying that there's not necessarily for prediction making purposes. Like, I don't think this will help you make a new diagnosis of diabetes, but this is just saying that like, in order for the model to predict the next token, and if it predicts diabetes, it's looking at kind of the relevant parts of the EHR. The parts that are kind of related or correlated with it, which obviously is use of insulin. Also something to kind of keep in mind is like the causality of these things. In terms of performance, the basic takeaway is just these models are better on a number of downstream tasks. So On the right-hand side is the foundation model, CEHR BERT. Here in this column is the same model, CEHR BERT, but without any pre-training. And then on the left is kind of, your standard tree-based models, LSTM, logistic regression. And, basically just kind of the takeaway from this slide is there are performance gains from using the foundation model approach. Same thing here with MedBERT. So the orange line is the foundation model. The other lines are the baselines. And what you see here is, it outperforms the baselines. I'll say the interesting thing is actually in the few shot setting, it seems to do worse. But that's something I'll address with a later work that we did where we do see better few shot performance with the foundation model approach. And then just to give like a super quick summary of the literature, so we do see that, certain of these models, if you train them the right way, which is the red line here, is the foundation model we train. They are better across, all label amounts than baselines. We do see that they're better on a diverse range of downstream tasks. So here, the foundation model is blue. The strongest baseline is in red. And then we did this across 15 different tasks. Same model. And then these works also showed that foundation models appear to be more robust to shifts due to time. And so if you're dealing with something like, you're training for a few years and then you're making predictions in the future, there's always shifts in, how medicine is practiced. Like COVID would be a great example, right? Like that was a pretty big shift in the distribution of patients. But even without a pandemic level event like COVID, there are still like shifts in your patient population, disease prevalence, things like that. So you want your model to be robust to that. And so just kind of the takeaway from this slide, I'd say is just these models do tend to perform better than task-specific models or kind of traditional methods. Maybe I'll pause there. Any questions about what I've said so far or things people disagree with? That's also totally welcome. Yeah.
So is there any, like, in terms of the amount of data available, intuition on, do we need more to be able to generate in a reasonable way, or is it actually like generate reasonable?
Yeah. That is a great question. I probably won't be able to get to this, but I'll share a paper that I think was put out by Columbia where they did do the generations and they compared like population level statistics against real world data set they had. And they did find like decent alignment. I think the question of synthetic data is like another one, like how valuable is that if you're training these models? But in terms of like, yes, if we roll these out and compare the population level statistics to real world data, I think there is decent alignment right now. But like, yeah, would I train a model on synthetic data now? Probably not, but I do think there is decent alignment. Yeah. And I'll share that paper after this as well. Yeah.
This question, in particular in this section, but kind of relevant. How do you deal with patient privacy? I know in the United States,
yes,
there are many complicated laws around this. How do you deal with that? Just by anonymizing? I don't know if that's enough.
That is a really good question. So I'll give a couple answers. So one, yeah, super hard to share data across institutions. And I think going back to the original slide about natural language versus EHR data, right? Even if theoretically there's trillions of EHR tokens in the US, you're never going to ever aggregate them in the same data set, the same way you would for like the pile or anything scraped off the internet. And so really EHR data sets are like roughly of the scale of 5 or 10 billion tokens. And so you're kind of stuck with that. So yeah, I do think that's an issue. And I don't think any hospital will ever share their full data set across institutions. In terms of like the research that we do and how hospitals have been able to do this, we typically almost always work with de-identified data sets. And so there's like an IRB, at least at Stanford, that says, okay, if you're working on this de-identified data set, you're allowed to train models on it. And then previously, so you're allowed to train models on it and work with it. In terms of like actually publishing stuff, actually that's the next slide. So I'll talk about publishing stuff in a second. So good question. So great segue. So how do we evaluate these foundation models once we've trained them? So to get to this question, it's really hard because you can't share the data, and there's concerns about sharing the models themselves, right? If they can generate realistic patient timelines. That's a big reason actually why, again, we chose to work with structured EHR data rather than clinical text. Clinical text, really, really hard to de-anonymize. At least at Stanford, they did try to do like automated de-identification. But I think in order to actually release data, it needs to be human verified, like every word a human needs to go over it. And so right now it's impossible to release any sort of clinical text-based thing, even if it's de-identified, unless you get a skilled human annotator to review every word. With structured data, it's a little bit easier because these are just codes, so they're a little bit easier to de-identify. And so we went through that process with Stanford over the past year in order to release this data set that I'm just about to talk to you about. But that is a reason to work with structured data. It's just a little bit easier to share. To kind of follow up on this question, so if it's impossible to share data and most people don't publish their models, how do you verify what works and what doesn't? And the answer is you can't really. So the field is kind of suffering from a reproducibility crisis. So this was a paper that we put out last year, so I'm sure these numbers have gone up since then. But basically, there were roughly 34 papers that had published their own EHR FM results. Of these papers, only 25 released public code. Of those, only 4 released any sort of weights of their model. Maybe it wasn't even the full weights, maybe just like a task-specific head or something. And then, none of these put their models on Hugging Face, right? So it's super, super hard to actually validate or compare fairly these models against each other. Each of these models is trained on their own institutions, private data set. So like the pre-training corpus is different. Like it's basically impossible to do an apples to apples comparison. And then the tasks that they work on are also usually derived from the same hospital-specific internal data set. And so even the benchmarks and the tasks are defined differently. So that's kind of a big concern of the field is how do we reproduce any of this work? I spent the last 30 minutes, praising these foundation models, saying they're great for all these things, saying they do few-shot learning and they're robust and blah, blah, blah. But, why should you take my word for it? And unfortunately, I don't think you can maybe run one of these models on your own, but it would be impossible for you to verify. And then even within the studies that people do, there are limitations, right? Like this first one, it was only done at one hospital, right? Because it was impossible to get data at another hospital. And when I say impossible to get data, I mean like at the scale that you need to do pre-training, right? Like hundreds of thousands, millions of patients, right? A lot of these data sets only look at one specific subset of the health record, which is like intensive care unit, ICU, or emergency department, ED visits. And so they don't really consider like the longitudinal nature of health records. The reason for this is that the main public data set, Mimic, only looks at really the ICU and the ED. And then again, the models aren't public, so there's no way to verify or, build on what they've done. So a lot of benchmarks for EHR data have been developed. So here's just kind of a sampling of very popular benchmarks. Unfortunately, like I just mentioned, they typically offer a very narrow viewpoint of patients. Almost all of them are sourced from a single data set called Mimic, which Mimic 3 has 40,000 patients from one hospital. Mimic 4, an improved version, has 400,000 patients. But, I don't know, it's just kind of crazy to think about like the last decade of ML for healthcare research that focuses on EHR data, at least. Basically, every result has been derived from this set of 40,000 patients from like one hospital's ED and ICU, right? So very narrow view of what makes a model good. The number of tasks that folks evaluate on is typically very few, and it's typically the same tasks every time. And so you're missing out on a lot of the greatness that these foundation models offer, right? Which is you train it once, you apply it to any downstream task you want. If we're only evaluating the same 3 tasks every time, we don't really get a sense of what is their generalization abilities. They don't really consider few-shot evaluation. And again, none of these release public model weights for the challenges that were mentioned in the question. And so that kind of motivated the last part of this talk that I'll very briefly talk about, which was work that we published earlier this year, last year, which was a benchmark called Earshot. And basically the goal here was to provide more representative data, just a new data set that was a little bit more geared towards evaluating foundation models for structured EHR data than some of these previous data sets, which had been developed before that kind of paradigm existed. And so what is Earshot? It's basically a data set of 7,000 patients. They're full longitudinal EHRs, just the structured data within them. So there's no clinical text. So that's kind of the data set component. There's 15 tasks that we define. And then there's also the weights of a foundation model that we pre-trained on 2.5 million patients at Stanford on the de-identified data corpus that had been IRB approved. And so what are kind of the components of this data set? Like I mentioned before, there's the 7,000 patients, which are the data set benchmark component. There's 15 different clinical tasks that we define on these patients. And then we also released this foundation model on Hugging Face with pre-trained weights from 2.5 million patients. And then I kind of hinted at this slide earlier in the talk, but basically we see that, this foundation model is really good. And it's not just good, but it's good in both, very low label settings. So, we go to like one-shot learning, which is pretty ridiculous for this setting, but, even, 24, 32, 48 labeled examples, which feels, more reasonable, there's still, gains to be had with the foundation model over traditional methods. And, they're fairly consistent across all 15 different tasks. And here I'm just kind of showing averages across tasks. And basically the takeaway is just, this is a good model and it can be adapted to a lot of tasks. So like we pre-train the model once and then we fit very lightweight linear head on top of it for each task, but the base model stays the same for every single task. And so we do have a leaderboard. I guess now that I'm in the shameless plugging portion of this talk, I would encourage you to download our data set and submit your results, and we'll throw your results on this leaderboard if you submit model results. And the data set, model weights, and code are all available at our website here, earshot.stanford.edu. And we encourage folks to apply for access. It's pretty straightforward, and work on the data set with your models. So what does this mean for hospitals? Just to very briefly conclude, I think the main takeaway from at least my experience working in this field is that foundation models do have the potential to offer significant benefits. We mostly focused on like accuracy and performance in this talk, but there could be a whole nother talk on the deployment considerations that make this approach very appealing to a hospital, right? If I'm a hospital, I don't want to have 1,000 different machine learning models that could have their own biases, that could be giving mispredictions, that could be influencing care in ways that I can't control. That's bad. Instead, train one model, centralize it, control that model, reduce the burden on people to train their own machine learning models for their own specific clinical tasks, and then just give people access to that single model. And so I think in terms of deployment and infrastructure, this approach greatly simplifies things in a way that the previous paradigm of everyone train their own model doesn't really work. But I would say, given that I don't think enough people are working in the space. And I hope that this talk will at least inspire you to maybe follow up on some of these papers or think about how you could apply your own methods or architectures to this sort of data. In terms of modeling, obviously there's like a lot of complexity with EHR data that I haven't talked about, but just to get started, I would just think of it as sequence of tokens, sequence modeling, natural language. Let's apply the best state-of-the-art models we have to it and see what happens. In terms of data sets, these are, I'll share these slides. These are kind of the three of the more popular and accessible data sets. So Mimic, like I mentioned, EICU is another large data set. Again, it's just focused on the ICU. And then, obviously, shameless plug, our data set, Earshot. And then lastly, in terms of reproducibility, this is something we're trying to push on as well, is to share more models. Unfortunately, it is more complicated to actually publish model weights, but we're hoping that this encourages more people to provide their models in a way that's accessible and easy for researchers to build on. So with that, I'll thank you all for the time. Thank you, Ronnie, and the AI Seminar for hosting me, and happy to stay afterward if there's questions, and my contact email is here if you want to reach out. So thank you so much for the time. Appreciate it.
Good job catching up. We have 2 minutes if somebody wants to ask a question now, feel free to stay afterwards if you have the time. If you have a question.
Yes.
What do you think about vendors across hospitals? They have access and it's decentralized and on the model.
Yeah, so it's a great question. So the federated learning stuff, I'm not an expert on. I think you still have the problem of different hospitals have different coding practices, and so that will be an issue. But again, I do want to highlight that tokenization slide with the text. I think that stuff is super cool. I'll share a couple papers that lab has put out, and I think that's a very promising approach to get models to generalize in a way that avoids a lot of the interoperability issues. Yeah, the papers are Uni HPF, Gen HPF. And it's Edward Choi is the professor on it. Yeah. 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 Yeah, so I think that's a really good question. Yeah, so I think that's definitely an issue. And then I didn't get to this slide, but there are some other unique aspects of EHR data that do make this complicated. So to your point, like there's a lot of what's called copy forwarding in the EHR. So like old diagnoses get copy forwarded. There's a few reasons for this. Like one is billing. But like, if you have a diagnosis, like, you still have if you still have cancer, so it's going to get recorded again in the EHR a lot of times. And so like, in addition to like other diseases influencing the model, like literally just the repetition of tokens that have no new information content can also kind of screw with the model in some ways. So like, that's something that needs to be handled as well. And I think, I mean, I like modeling wise, like I think the answer is just, oh, like hopefully attention takes care of it. But yeah, I think, smarter things can definitely be done with that for sure. But I think the hope is, self-supervised learning, the model just kind of learns to pay attention to the right things. Yeah. Cool. Any other questions? Happy to quickly go through the Zoom ones too. I think there's just a few. Is this currently deployed at Stanford Hospital? No, this model is not, but we're working on that right now. How do you decide total number of parameters? Great question. The 140 million just seemed like a good kind of base to start with, but I actually don't think I've seen anyone do like the full scaling curve thing. So if folks are interested in that, that would be an interesting question. Like what happens if you train these to 1 billion parameters? And then, yeah, the tokenizer, I think I answered this before, but yeah, numerical values, I think still an open question, but typically people just decile them and give each decile a token. Yeah.
Related to that scaling question, do you know, like, I don't know if you've done this or have done something to look at this as you increase the amount of training data for the foundation model, like how much better is the accuracy or performance getting? Like,
Yeah.
You could easily do that, right?
Yes.
You essentially train on less data than use the full amount you have. Like, is the improvement kind of slowing down over time?
That's a really good question. Yeah, we haven't published anything on this, but at least in my experience, I've seen like definitely after one epoch, you're basically done. And then and an epoch in our case is just going through every patient in the data set. And even before then, it kind of saturates. I think a large part of that is because if you remember that chart, like most patients have like 100 events or something super small. And so I think, so yes, it does saturate very fast, but I think one of the big gains that will hopefully be had is getting longer patient timelines that will require pooling data across institutions or doing something where you have more access to data. I don't know the solution for that, but yes, I do think like we are a little bit limited by the scale of the data set that we have, which is really not that much. Yeah. If that answers your question.
I mean, I guess I'm also trying to get this question of whether you have a sense of like, if Stanford were to magically have like 10 million patients,
Oh,
right? Like where you have a lot more tokens. Like, are we getting to a point where the performance is like?
oh, the performance saturates. Yeah. That's a great question. I don't know, but my sense from looking at benchmarks is like we're pretty close on the tasks that we're looking at. Like people have done like inpatient mortality to death, like 30-day readmission, like everyone's looked at that. So I feel like some of those tasks are probably saturated, but I think there's like hundreds of other tasks that you might care about that no one's looked at. Like at Stanford, for example, like early PAD detection, right? Like that's a task that like, I don't know who's published on that, maybe a couple people. Like that's a cool thing, right? Like there's some like financial modeling things people are interested in. Like I think, I think the 3 tasks that most people evaluate on, I think actually are like, if you look at the changes in model performance are getting smaller and smaller. But I think there's a lot of other tasks that people should start coming up with now that just like, in NLP, like once the benchmark gets saturated, people come up with another benchmark. Like I think there needs to be more of that. And I think that's been hard in this space because tasks are so hard to define and it's also really hard to share data. Yeah.
Can you go slide with the data set, EHR term, and the
Yep.
2 models?
Yes.
No, the 2 models, the foundation model and the one general.
Sorry, which slide was that?
The foundation model and the one generalized with 50 tasks.
Yeah, this slide.
Yeah, one before. Yeah.
This slide. Okay.
So what are the tasks you guys downstate train on there?
So that's a good question. Off the top of my head, so operational outcomes is like the 3 tasks that I just criticized. It was like 30-day readmission, inpatient mortality, and ICU transfer. Lab tests, it was 5 lab tests where it was the task is, will this lab test come back abnormal or not? So like basically, should I order the lab test or not? And the application is we're interested in reducing waste in the hospital. New diagnoses, this was a set of, I think, 5 or 6 ICD codes, where we were trying to predict, will you get this diagnosis within the next year? So it's like pancreatic cancer, hypertension, something, and then chest x-rays. This was slightly different. This was a multi-label task, where we had 14 different potential class labels. And the task was, you're going to predict right before somebody has a chest x-ray done to them, of the 14 possible labels, which will the chest x-ray report come back with? Those labels were not available in the structured EHR. Instead, we used the clinical note for generating that label set. So we don't release the clinical text, it's just the labels. And those labels were taken from the Chexpert paper, if you've seen that. And so the interesting thing actually about the chest x-ray task is, in contrast to these tasks, which all live in the structured EHR, this task, the labels actually only live in the text. And so it's kind of cool that the model is able to anticipate or predict these with, again, decent accuracy-ish, even though like the true labels and the actual modality that generates the labels is images and text. So the model doesn't see any sort of that data.
We can continue these exchanges.
Yes.
But let's declare this